Hello, good evening. Hello, everybody. Today's lecture on square wave permanent magnet versus DC motors. Here, the square wave permanent magnet versus DC motors comes under the category of a permanent magnet versus DC motor. Here, square wave and also sine wave. We're having two different topics. The square wave, which is related towards the, and sine wave, which is related towards the EMF, generation of EMF in the motor. Here, the square wave is having that 120 degrees displacement and also nothing but 120 degrees of operation and also 180 degrees of operation. Both we are having. Now, before going to that, we will observe that about the permanent magnet motors and also what are the advantages and disadvantages and some of the principle of operation we can observe now. Here, in the introduction, the topics that are covered is permanent magnet machines and the principle of operation of a permanent magnet machine. And next one, operation of a permanent magnet machine supplied by DC to AC converter with 120 degrees mode of operation. We previously discussed about that, nothing but one degrees of modes of operation, types of modes of operation. We are having two types of modes of operations. First one is a 120-degree mode of operation, and the next one is a 180-degree mode of operation. Both are DC to AC converter here. Okay, and the next one, if we one by one we the topic one by one we discuss here, that is permanent magnet machines. By using of these high energy magnets such as rare earth based magnets. These are rare earth materials or is also called rare earth metals. Here, by using of these high energy magnets of rare earth based magnets, a permanent magnet machine drive, a permanent magnet machine drive can be designed with a high power density, high speed and high operation efficiency. In yesterday's session, we discussed about the topics of electrical transportation. Nothing but so many electrical transportation vehicles of two wheelers and four wheelers are now designing. Here, the motors are based upon the permanent magnets. Nothing but no field system of using a winding, copper winding using the field system is not using here. Here we are using that within the field system. We are using that only the permanent magnets. With respect to that, by using of the permanent magnets only, the motor can be operated. Okay, next one. These permanent magnet machine drive can be designed with high power density. First one is next one high speed and high operating efficiency. These three conditions are must and should be followed while using these permanent magnet machines. Here, the advantages are attractive for their applications in electrical vehicles and hybrid electrical vehicles. Nothing but these topics are nothing but what are the advantages and what are some of the disadvantages also we are having that. Here, these all are considered for major applications of electrical vehicles and hybrid electrical vehicles. Nothing but if you observe here, this is EVs. EVs is nothing but the electrical vehicles and HEVs, that is hybrid electrical vehicles. Hybrid is nothing but a combination of these two engines. That is one is electrical engine and the next one is a fuel engine. Okay, that is a petrol or a diesel. Next one, the major advantages of these permanent magnet machines are we're having major advantages. What type of major advantages we have to uh, operate that motor? Here, if you consider high efficiency, the permanent magnet machines have very high efficiency due to the use of permanent magnets for excitation, which consume no power. Example, first one, if you use in any AC machine, if in case of using the AC machine with AC supply, and also without using any permanent magnet, suppose here, what should be happen? Some losses are there of a rotor copper losses and also the iron losses. Here, within these permanent brushless permanent magnet motors also there these losses, but losses will be reduced. due to the field system. With respect to the field, the losses are reduces. So while we're going to this choose this permanent magnets, here best one is the high efficiency, nothing but the high efficiency machines have a very high efficiency due to the use of permanent magnets for excitation purpose. For normal, we are going for winding. Whenever you are using the winding means, therefore the size of the motor has been increased, and also the losses, field copper losses are increased, and also iron losses also somewhat increase. Next one, the absence of the mechanical commutators and brushes results in low mechanical frictional losses. This is the best advantage while using with a permanent magnets and also brushless. Okay, mechanical commutators. Okay, in the absence of mechanical commutators and also the brushes, while we are eliminating these two main parts of the normal conventional DC motor compared to towards the permanent magnet DC motors, here the frictional losses are reduces. Therefore, there is no noise, and also whatever the output shaft output power output should be increased value. So that's why the efficiency value, while reducing the losses of frictional losses, iron losses, and also somewhat field copper losses, while all these losses are reducing means, therefore automatically the efficiency of the machine drive can be increases. Next one, high power density. If you come across this high power density, the most important another parameter is nothing but also the density, power density, and also the torque density. How much value can be produced by the to drive that particular mechanical load. Okay, if you think about these two wheelers now the two wheelers are designing with lithium ion batteries and also 1000 watts motors and also 750 watts motors, 700 watts motors. While using these type of motors, with respect to this with respect to of when a load is increasing, suppose when load is increasing, if you observe, with respect to that particular load value, the torque is also increasing. Nothing but what about amount of the torque required by that particular motor can be overcome. Okay, so the power density is the term. The high energy density or high power density magnets has allowed to achieving very high flux densities in the permanent magnet machines. As a result of high flux densities, high torque, very high torque can be produced from a given volume of the motor compared to other motors of the same volume. That is the major difference. Nothing but we have a doubt also. Whenever permanent magnets are using, flux value is to be a constant value. Yes, that is a constant one. There is no other change value. Nothing but if you come across the conventional motors, the whenever the field is using here, with respect to the field is using here, the field value can be increased, or the flux value can be increased with respect to the current, where current can be changed by using a rheostat, normal rheostat. But what is the major difference means here, while using with the permanent magnet machines as an excitation for the motor, therefore here the motor capacity can be reduces at the same time with this nothing but the size of the size of the motor can be reduces with using of the permanent magnet excitation machine drive. But what should be happen mean, with respect to the whenever the size of the capacity increasing means, equally the power capacity is also increases, or a power density can be increases. There is a possibility. Why? Because so many uh, advantages has been happened, take considered on that particular machine. That is the winding, whenever the if you're using armature winding, if you are using permanent magnet permanent magnets as the excitation. Okay, here what should be happen means, with respect to the conductor size can be varying, a winding of the conductor can be varying. Therefore, what should be happen means, equally the torque can be increases. That is, the power density can be increases. That is the difference. As a result of high flux densities, high torque can be produced from a given volume of a motor compared to other motors of same volume. This is the important one. Okay, given volume of the motor compared to other motors of the same volume. Next one, ease of control. This is the main important another parameter of controlling. While we are running any motor, with respect to that particular motor, with respect to that load on that particular motor, if the motor has been used, when the load is varying, nothing but if you are using running with a two-wheeler vehicle, if you are running, we are started with a one person has been started, and it should be running with some distance from 0 kilometer to 5 kilometers. After 5 kilometers, another person has been added. Suppose the weight of the person should be 120 kgs, both 60 60. So what should be happen, whenever the load on that particular motor has been increases, means what should the torque required by the motor is also increases, torque required. So, and the control of that particular motor is also very necessary. So ease of control. The permanent magnet motors can be controlled as easily as DC motors because the control variables are easily accessible and constant throughout the operation of the motor. These, the major within the electrical vehicles transportation, we are using a BLDC motor, brushless permanent magnet DC motors, and also the controllers. Whenever using the controllers means the controllers is also play an important role. Why? Because without we are you increasing the accelerator to increase the speed. So what should be happen means the controller is also the most important value. So by using with the permanent magnet motor, a BLDC motor on that particular load, here ease of control is a possible. Ease of control means the control over the motor has been very easy. Next one, some of the disadvantages also there. Some of the disadvantages also there on that particular permanent magnet brushless DC motors. Here, uh, that is, the permanent magnet machines also suffer from some disadvantages such as cost. Very important. That is the cost. Rare earth magnets commonly used in permanent magnets are very expensive. These these rare earth magnets are making with an alloy materials. Wow, for all Nico, all these materials we are adding these all these materials and making into a costly magnet. Nothing but costly means in the sense that is that can be produced. If suppose if a permanent magnet has been taken, that the permanent magnet has been given a lifetime to produce the flux value of 30 milliwebers, 30 milliwebers for a time lifetime of 5 years, suppose. So that particular motor can be produced up to 5 years, this much value of the flux. Okay, not only the 5 years, it should be 10 years also. Why? Because the motor cost is should be that much. That's why that much cost should be increases. That depend upon the magnets, permanent magnets which are used for the excitation purpose. That is a very important value. So in a BLDC motors, permanent magnet brushless DC motors, the important parameter, the important uh, material is also a permanent magnet in the rotor. Next one, magnet demagnetization. The magnets can be demagnetized by large opposing magnetomotive force and high temperatures. These terms are occur in the these terms are occur in the these terms are occur at a materials, magnetic materials. Nothing but we are using different types of materials, soft magnetic materials, hard magnetic materials, and also different types of alloy materials. Here, the rare earth magnet materials comes under the hard magnetic condition, hard magnetic classification. Here, magnet demagnetization is also which we consider now. That is, whenever the excitation has been given, whenever the excitation has been produced by the flux, sorry, produced by the rotor by using of a permanent magnets, here within the stator also here, within the we are using the winding, armature winding. Here, with respect to interaction between these two, fluxes and EMF is also produces. That is a back EMF or a counter EMF that which opposing the main flux. Main flux, that is the magnet demagnetization. The magnets can be demagnetized by large opposing magnetomotive force and high temperatures. The next one, inverter failure. Due to magnets on the rotor, due to magnets on the rotor, permanent magnet motors present major risks in the case of short circuit failures of the inverters. Here, the rotor is always energized and constantly induces EMF in the rotor short-circuited windings. A very large current circuits in those windings, and accordingly, torque tends to block the rotor. The dangers of the blocking one or several wheels of a vehicle are non-eligible. What type of inverter failure? What is the condition of inverter failure here means? Due to the magnets on the rotor, we are using the permanent magnets on the rotor of a BLDC motor. The permanent magnet motors present a major risk in the case of short circuit failures of the inverters. Nothing but there is a problem of getting inverters short circuiting. Inverters means either it is converting a DC to AC also or AC to DC also. We call it as inverters. But here the major condition is to be whenever inverters are comes under the failure category, failure condition, that is a short circuited of inverter. Therefore, there is a problem. There is a problem of a major problem is to be um, wheels can be block. Wheels can be block of the BLDC motor. Next one, based on the shape of the EMF, back EMF induced in the stator windings, the permanent magnets motors can be classified into two types. Here, the EMF is having that the back EMF is induced. The back EMF is induced within the stator of the motor, BLDC motors. Here, there is a classification. That is, first one is a permanent magnet synchronous machine with a sinusoidal back EMF, permanent magnet synchronous machine with a sinusoidal back EMF, and next one is a brushless permanent magnet DC machine. Brushless permanent magnet DC machine with a trapezoidal back EMF. These two conditions we consider. Okay, BLDC, brushless DC motor, brushless permanent magnet DC machines with a trapezoidal back EMF. These are practical one. Okay, these are the practical one. These are the sinusoidal is a normal one, and this is the practical one we observe. Based on the construction of the rotor, the permanent magnet machines can be broadly again classified into three categories. Construction of the rotor: inner rotor machine, outer rotor machine, and interior magnet rotor. Here, the back EMF is to be generated in the form of trapezoidal. Now, in practical applications, we observe these all the EMF within the motors. The EMF generation is to be a back EMF is to be in a trapezoidal manner. And next one comes towards the classification of the permanent magnet machines based on the rotors, inner rotor machine, outer, how the classification should be. And this is the picture which shows that classification of the permanent magnet machines, that is inner rotor machine, outer rotor machine, and interior magnet rotor machine. Inner rotor machine is nothing but the, here if you observe here, this is the, here if you observe, this is the uh, armature winding, or it is a stator. This is the stator winding or stator slots which has shown here, and next one is the rotor, and this is nothing but the rotor with the permanent magnets, that is the inner rotor machine. Nothing but the rotor which we are placed is to be in inner, and next one is outer rotor machine. Outer rotor machine which consisting of these are the stator slots and the slots which consisting of the winding. Here the stator slots above, nothing but over the stator slots, the rotor winding has been used. Sorry, the rotor magnets has been used. That is nothing but the rotor outer rotor machine. These are nothing but the permanent magnets. These are nothing but the permanent magnets. And next one, interior magnet rotor machine. Interior magnet rotor machine, which is consisting of here north pole. Here, if you consider, this is the north pole and this is the south pole, and this is the north pole, again this is the south pole, suppose here. But what should be happen, the permanent magnet itself having that north and south poles. This is nothing but the interior magnet rotor machine. Interior magnet rotor machine. And next one, and next one what about the principle of operation? About the principle of operation, here the principle of operation, which this is the classification of the construction of permanent magnet machines, and this is nothing but the principle of operation of a permanent magnet machine. The torque produced, the torque produced in a motor, in general, a rotor flux and a stator MMF has to be present that are stationary with respect to each other. The rotor flux, nothing but the permanent magnet is nothing but the rotor. Okay, the rotor flux and the stator MMF, magnetomotive force, has to be present that are stationary with respect to each other, but having a non-zero phase shift between them. That are stationary with respect to each other, but having a non-zero phase shift. Okay, and in permanent magnet machines, the necessary rotor flux is present due to rotor permanent magnets. Currents in the stator windings generate the stator MMF. The nothing but with respect to the interaction of the rotor flux, then only the stator windings can produce an EMF. That is stator MMF, magnetomotive force, and then we are getting the stator EMF. Okay, that is called a back EMF. The zero relative speed, nothing but relative speed between the stator flux and also the rotor flux, and that is also called a stator MMF and rotor MMF. Rotor flux, stator flux and rotor flux is to be having that zero relative speed. Here, whenever if the stator MMF is revolving at the same speed as the rotor flux, that is rotor speed and also in the same direction, rotor speed and also in the same direction, then the revolving stator MMF is the result of injecting a set of polyphase currents phase spread from each other by same amount. Here, the phase shift between the polyphase windings. So, for example, if you consider a three-phase machine, nothing but if you observe, this is the classification of the machine. We are observing now that inner rotor machines. Most of the motors are inner rotor machines only. Most of the in practical, most of the motors are inner rotor machines only. Nothing but the inner part we are having that permanent magnets, and outer part over that over that permanent magnets we are placing the stator winding and stator slots and stator winding. Here, whenever the flux produced by the permanent magnets, here these flux cuts the armature conductors, and the MMF stator MMF can be produced, and also an EMF is produced within the stator, and then by the torque. Here, next one, a three-phase machine. If you consider the three-phase machine with three windings shifted in space by electrical 120 degrees between them, produces a rotating magnetic field constant in magnitude and traveling at an angular frequency of the currents. We are considering that a three-phase machine. For example, a three-phase machine with the three windings shifted in space by electrical 120 degrees between them produces a rotating magnetic field constant in magnitude. Magnitude is constant, I think, but the flux magnitude is constant and traveling at an angular frequency of currents that is same as that of the induction machines. We are considering as an AC machine. The rotor has a permanent magnets on it, hence the flux produced by the rotor magnets start to chase the stator MMF, and as a result torque is produced. This is the working principle of permanent magnet motor even for an induction motor. The rotor has a permanent magnets, hence the flux produced by the rotor magnets start to chase the stator MMF, and as a result torque is produced. Since the relative speed between the stator MMF and the rotor flux has to be zero. Actually, the relative speed difference is to be having a difference value in induction machine, but it should be here zero. The rotor moves at the same speed as the speed of the stator MMF. Hence, the permanent magnet machines are inherently called as a synchronous machines. I think, but these are uh, discussing about that permanent magnet synchronous machines. Whenever we are discussing about the synchronous machines and induction machines means comes under the AC category, alternating current supply category. Even for the rotor is having with an excitation with a DC, but having AC supply of the three-phase winding. So what should be happen means it comes under the category of synchronous machine category of permanent magnet machines. Here, as the coils in the stator experience a change of flux linkages caused by the moving magnets, there is an induced EMF in the windings. The shape of the induced EMF is very dependent on the shape of the flux linkage. If the rotational electrical speed of the machine, suppose considered as a omega r value and the area flux is a sinusoidal, then the equation can be pi is equal to pi m sin omega t. And omega is nothing but the angular speed value, and it can be written in the form of np by 2 omega mechanical. Nothing but we are connected towards electrical. Omega r is nothing but omega e or r, electrical speed, and also omega mechanical means omega mechanical speed of the rotor. Here, if you consider about the flux linkage and also the back EMF, flux linkages and back EMF. Here, if you observe, this is nothing but the flux. This is nothing but the flux. This is the flux, and next one, flux produced by the suppose it is called as a rotor, permanent magnet rotor. This is the flux, and next one, this is nothing but the EMF value or the back EMF. Here, if you observe, from zero, it should be increasing. The flux value is to be increasing up to the maximum value of 90 degrees. The maximum flux can be getting at a 90 degrees value. At this position, the EMF is to be zero. Okay, the flux linkage is to be in parallel. So, therefore, the flux linkages with respect to the conductor uh, is to be zero, parallel. So, that's why the EMF is to be zero. The EMF produced is to be zero. So, whenever that after decreasing of the flux value from 90 degrees to 180 degrees value, whenever that it should be maximum value of the EMF produced on the negative side. It is on the negative side, and also and furtherly it should be increasing from zero. The maximum flux will should be maximum value of it with a 1.0, or it is also called a 10 volts. It's denoted with a 10 volts value. So the voltage value at 1 milliweber flux or one value of the flux linkage, it should be 10 volts. Okay, so with respect to that, the flux linkages and back EMF of a synchronous machine has been observed. How the waveforms and also how the back EMF with respect to the flux. Next one, if you observe the number of turns, the number of turns, and also think about how the EMF can be produced. Number of turns and the flux linkages lambda are equal to the product of n pi. The induced EMF is equal to the rate of flux linkages and is given by that E is equal to minus d lambda by dt, and which is equals to minus n times pi m omega. We substituting that lambda is the value of n pi. Pi is nothing but the pi m sin omega t. Here we are changing with respect to we are changing with the sign value and given with a minus one minus sign here, and the sign has been replaced with the cos value. So that's why we are getting the minus value minus n pi m omega cos omega of t. And next one, by differentiating that, we are getting the equation minus lambda omega r cos omega r t, and which is also written in the form of minus lambda, and lambda is nothing but the combination of n pi, product of n pi. So that we are getting that E is equal to minus lambda omega r cos of theta r, and theta r is nothing but the product of time and also the electrical speed of rotation of the rotor. Here, if you observe the negative sign in the equation value, that indicates that EMF opposes the applied voltage. We are applying the voltage from the stator side. Here, with respect to that, we are getting the negative sign. That denotes that induced EMF opposes the applied voltage. And next one, the EMF is proportional to the product of the rotational frequency and air gap for a constant number of turns. The directly nothing but back EMF is proportional to the product of rotational frequency and also the air gap for a constant number of turns. Next one, assuming that air gap flux is constant, it can be seen that EMF is influenced only by rotational speed of the rotor omega r, that is in terms of electrical value, which is same as that of the stator current frequency. Here, by changing the frequency of the stator current, suppose we're giving that AC supply towards the stator winding, and permanent magnet has the DC. Suppose by changing the frequency of the stator current, the speed of the motor can be changed and the speed control of the motor can be achieved. However, beyond a certain speed known as the base speed, an increase in the stator frequency will result in the voltage demand exceeding the supply capability. Here, these are comes under the category of speed control. During that operation, keeping the voltage constant and increasing the excitation frequency reduces the air gap flux, and thus allowing the excitation frequency reduces the air gap flux, thus allowing going to higher speed over and above base speed values. This operation is known as a flux weakening method. Here, what these terms can be explained means, from the alternating current supply voltage side of the motor given towards the stator winding, there is a possible to control the speed, that is above base speed or below base speed values. So we always allow that change in the frequency value and also not the voltage value. Even we are changing the V by F ratio also. By changing the V by F ratio, there is a possible to change the speed of the motors, synchronous motor, permanent magnet synchronous motors. Next one, the permanent magnet machines are fed by DC to AC converter by changing the frequency at which the gates are turned on. The frequency of the output wave can be varied. Next one, the some of the assumptions are made for the 120 degrees and 180 degrees mode of operations of the permanent magnet synchronous machines. Here, the phases of the machines are star connected. The current entering the neutral point is considered to be positive and leaving it is considered negative. The back EMF induced in the phases is sinusoidal. All the phases of the machines are balanced. That is, the inductances of and the resistances of the phases are equal. These are some of the assumptions which are made for 120 degrees mode of operation and also the 180 degrees mode of operation. In the next session, we will discuss about that 120 degrees and also the 180 degrees mode of operation of the permanent magnet synchronous motors. Thank you.